Hi, in this talk, I will present our research, Watch, Read, and Look Up, Learning to Spot Signs from Multiple Supervisors. My name is Liliane, and this work was done in collaboration with Gulverol, Samuel Albany, Trandafylos Ephorus, and Andrew Zessuman. Let's begin by introducing our task. Given a dictionary video of an isolated sign of interest, for example, the sign strong, and a continuous sign language video sequence, our goal is to automatically determine where the sign strong appears in the continuous sequence as shown next. Note, there will be a color change. Prior work on this topic are listed at the bottom of the slide. This ability to spot signs has a broad range of applications. Examples include making online signing videos searchable, building tools to support sign language learning, making voice-activated devices respond to signing, and building sign language datasets by automatic sign annotation. Some key challenges in this task include the severe domain difference between isolated dictionaries and continuous signing in the wild, as shown in the following examples. In particular, they differ with respect to co-articulation in continuous signing, where the appearance of the current sign is influenced by the previous and next sign, and also differ in terms of speed, as isolated signs are usually performed more slowly. Secondly, there can be multiple sign variants corresponding to a single English concept, in this case, the sign before. Finally, dictionaries only possess one or a few examples of each sign. For instance, the sign orange has only 2 examples. So learning must be low-shot. We will first introduce the datasets, then how we solve the problem, and finally show some applications. To solve our task, we require both sources of isolated and continuous signing. In order to obtain a large vocabulary of isolated sign examples, we collect in this work online dictionary videos to form a British Sign Language dictionary dataset, BSLDict, which we make publicly available. An example is shown for the sign cake. BSLDict has a total of 14K video clips for a vocabulary of over 9K signs, where each sign has between 1 and 10 examples and may have several variants, and signs are performed by a variety of 148 signers. For our source of continuous signing, we use the BSL-IK dataset from our previous work, which is collected from over 1,000 hours of sign language interpreted TV broadcasts with subtitles of the audio content. The BSL-IK dataset has also over 270K sparse sign annotations for a vocabulary of over 1,000 signs, with 40 different signing interpreters. Let's now introduce our approach. Given a dictionary video and a continuous signing video sequence as inputs, our goal is to learn a joint embedding space from these 2 sources of data, in such a way that at inference time, the dot product between the temporally average dictionary embedding and the continuous signing embedding shows a high similarity score when the sign occurs in the sequence. We make use of I3D, a spatiotemporal convolutional neural network for the embedding architecture. In order to learn such a joint embedding space, we make use of the principles of multiple instance learning and noise contrastive estimation, whereby we collect potentially matching signs into a positive bag and encourage high similarity to 1 or more samples in this bag, and minimize the similarity between different signs, which we refer to as a negative bag. To form such positive and negative bags, we propose the watch, read, and lookup framework, where we make use of three sources of supervision: watching sign language and learning from existing sparse annotations, reading associated subtitles, which provide additional weak supervision, from which we can extract candidates for signs that we expect to be present, and finally looking up words in visual sign language dictionaries. Now let's look into how this framework is applied in practice by looking at a batch of size 2. Firstly, we start by watching sparse localized annotations in continuous signing video, in this case for the signs friend and language. We then extend the temporal window around the annotation to cover the duration of the associated subtitle. Secondly, we look up in the dictionary the isolated sign examples for the annotated signs friend and language. Finally, we read the subtitles associated with the continuous signing video and look up the remaining background words in the dictionary. Positive and negative bags are formed between the continuous signing and dictionary videos within the batch using 4 different anchors. We will next go through one of these cases. For example, for anchoring on the continuous signing segment labeled as friend, we define a positive bag as dictionary videos corresponding to the sign friend, and make all other dictionary videos in the batch negatives. Please refer to the paper for details on the remaining anchor definitions. The embedding network is trained using MIL-NCE on millions of such positive and negative bags. Now we compare against other methods by evaluating on the BSL-IK automatic test set with 264 sign classes seen during training, and computing the mean average precision over sign classes. Specifically, we consider 2 baselines: sign classification with the cross-entropy loss, and a single instance info-NCE loss. Our multiple instance NCE model with the watch-read-lookup framework surpasses both baselines with a mean average precision of 48%. We next apply our sign spotting framework to 4 applications: indexing for content-based search, sign variant identification, dense annotation, and Faux identification. Firstly, we show the ability of our model to help search through continuous signing videos. For the BSLDict sign shown on the left, we retrieve the highest ranked continuous BSL-IK sentence video clips, which contain the corresponding word in the subtitle. Secondly, we show the ability of our model to spot specifically which variant of the sign was used. For the continuous BSL-IK video clip on the right, we show the similarity scores for querying 3 BSLDict videos of the sign corresponding to the subtitle word animal. The first 2 dictionary videos match the sign variant and display a high similarity peak when the sign occurs. The last video corresponds to a different variant and shows low similarity. Thirdly, we show the potential of our model to obtain dense annotations for continuous sign language videos. For the BSL-IK video clip on the right, we show the similarity scores for querying 3 BSLDict videos of different signs corresponding to words in the subtitle. Finally, we demonstrate the potential of our model to discover Faux between British and American sign languages by retrieving nearest neighbors according to visual embedding similarities. Thanks for watching. Please refer to our paper for more detailed numerical evaluations and check out our website for more examples.